get our recording going again. All
Could you
right.
show us,
I'm sorry.
could you show us like how to do it? Because I used it from like the 8 things that we did, like the data from that.
Right. So this is what I do want to go over and show you how to redo this. So, all right. So let me do my screen share here. So if we go back to the original 8 circuits, this is what we had, right? So we were taking a look at these 8 circuits, and we noticed that in these circuits, everything had to be on. In this type of a circuit, right, in our series circuit, everything has to be on for anything to work. I'm going to dial up our voltage here just to give us a little bit more brightness in our bulbs. All right. Whereas over here, having the same voltage, right, we did not have to have everything on. So this bulb lit up, and it was much, much brighter than these bulbs, even though the battery is the same, even though I have 2 light bulbs and 2 switches. If I turned on this one, neither one of these affected one another, but over here, if I shut that one off, the other one shut off. So we have dependence in this circuit, independence in this circuit, where each branch is independent of the other branch. It doesn't matter what's going on with the other bulbs, whereas over here it mattered. But you notice that over here, even though I have the same battery and the same number of bulbs, the amount of current that is coming out and flowing in these wires is completely different than over here. This current over here appears to have very, very little energy, whereas over here they are moving very fast and seem to have even more energy. So we ended last class, we wrote all down the analogies of saying each bulb has to be on in this circuit, all the current is the same, and the voltage divides up. Over here, each pathway was independent of the other pathway. The voltage was the same across each branch, and the current split up at this junction where we had 2 different bulbs. So we ended class asking ourselves, what determines the amount of current that the battery would send out? What determines how much voltage is used across each bulb? So the intention was that you would go into your lab, and I'm going to remind you that if you take a look at your lab and the write-up, there's a part 2 that was specifically on its own page right here. Part 2 determined the relationship between voltage, current, and resistance. So here is what you were supposed to do in this lab. You were to set up this diagram instead. And instead of using a light bulb, you can throw in a resistor. All that we're doing in this lab is taking a look at the effect of different voltages on different currents. Okay, so we want to take a look at that. Just want to make sure nobody else is waiting here. All right, hold on. We got a couple people coming in our waiting room. Jack. All right. Matthew. Okay. All right, so gentlemen, if you are just joining us, so here's what I wanted you.
At my router.
Was y'all's internet screwing up?
Well, you know, it's so interesting. It's something with this class in particular, so I'm not sure what's going on. The only one we're missing, I knew Frankie wasn't going to be able to be with us. CJ.
Maybe there's a lot of people on at 9 in the morning or so, or 10 in the morning.
Well, I said my prediction was that if you think of time zones, Central Time, Eastern Time, Western Time, you know, the Pacific Time, I guess it's called, 10 o'clock is like the prime time because it becomes like 8 o'clock in most of the world. Anyway, in the United States, where we are using all the internet. So whereas our 9 o'clock classes may not be as crowded. But anyway, for Matthew and Jack, as you are joining us, I'm just discussing the lab that was due today. So it was a write-up that was at the end of this lab. And what you were doing, if I go back now and I share, you were to build not these circuits again. So you weren't to use this data because the only voltages that we had in circuits 1 through 8 was 6 and 12 volts. So that didn't give us a variety of voltage. So what you were doing was building a circuit like this, okay? when you build that circuit, so if this is done incorrectly, I will take off points and you're going to miss more points than turning it late. So I want to go back through this to remind you how to do it. Those of you that did not do it correctly, you're better off to redo. All right, and I will give you till Monday to have that done. So all you're doing here is changing the voltage, and I recommended you start with 3 volts. So using 3 volts, how much current is coming out when the resistor has a value of 10 ohms? So we know the resistor has a value of 10. So I have a current of 0.3. So I recommended that you use Logger Pro, okay? So this is the Logger Pro setup. Okay, so this thing always, I'm looking at, we have a thing called reconnecting coming in, and I feel like that is just, I don't know if that's somebody, because your names usually come in. So somebody text CJ and Ben and ask them if they're trying to get in. Because I'm not getting their names. All right, I'm going to continue on because that makes me nervous that that's what's screwing up our meeting here. All right, so what I did is I wrote down 3, and 0.3 was my current. You go back to the lab and you dial up your voltage. So I click on the battery and I change the voltage now. I'm going to double it to be 6 with 6 volts. Yes, go ahead.
Logger Pro is $250 for me to download.
No, it shouldn't be. It's
That's what
absolutely,
it
it
I have
should
a
be.
MacBook Pro.
Oh, I have to send you a different link. So is that Matthew?
Yeah, that's me, Matthew.
Okay.
Oh,
I'm glad you didn't do it. I will send you a different link for your Mac.
I have the same problem.
Okay, Jack, I'll send you a different link also.
Look up Logger Pro for Mac, and it's the second link.
Yeah, it's a different link. It does look like it should not cost any money whatsoever. All right, so hopefully we have Ben. All right, so now I have 6 volts, 0.6. If I dial this up to 9, you can see the pattern, right? If I go 9 volts, I get 0.9 amps. So as I increase my voltage by 3, my current increases by 0.3. So when I go through and I do the lab, here's all my values that I put in. As you punch this into Logger Pro, so this one would be 3, it automatically graphs for you. So I automatically get the graph. When you click up here, this is the format that went with our motion detectors that was in the lab. So all I have to do is click right here and it gives me the linear fit. So on my x-axis, I have voltage. On my y-axis, I have current. My slope is 0.1. If I go back to my lab, my resistance was 10. So 0.1 is the inverse of my resistance. Okay, so let me remind you, because I'm going to stop my screen share. Here's the data that I got. And again, I don't want you just copying this. So everybody, if you redo this lab, you are not allowed to use these exact same numbers. Make your voltages different. Say that again.
Where'd you get like 30 and 27 from?
Where are you
I
getting
just made that up. You are in charge of the voltage. So when I go back to my circuit right here, I am controlling the battery. So if I click on the battery, I get to choose how much voltage I want it to be. So I went up by 3s. I went 3, 6, 9, 12, and so on. That's my variable that I'm changing. That's the independent variable in the lab.
So where do you get the other number?
The dependent variable, the current. Right here, you see my meter?
Oh, yeah.
The ammeter. So I stuck it in there. So as I dial up my voltage, and literally, this should take you 10 minutes to do. So I go to 10 volts. What's my current? 1 amp. I go to 12 volts. What's my current? 1.2 amps, right? So my point is, I wanted you to put together everything we studied all year, which is, here's data, here's a straight line, what is the meaning of this slope based on what I graphed? So I have voltage versus current, and I got a slope. How does that slope relate to other variables that are in my circuit? And the only other variable in my circuit is my resistance right here. What would my data look like if I changed my resistance? If I make this now 20 ohms. So if I dial this up to double my resistance, and I go back and I take a look at when my voltage is 3 volts, my beginning, right? So what we're trying to do here is trying to figure out what is the effect of voltage, current, and resistance. I see that I ended up getting half the amount of current. My original data, when I had 3 volts, I got 0.3 amps when my resistance was 10 ohms. But when I changed my resistance to be 20 ohms, I changed the current. So there's a relationship between voltage, current, and resistance. Now, everybody looking at the computer simulation on there, look what happens when I change my resistance. What's happening?
When we get on the application, is it intro or lab?
I'm sorry, say that again?
Is it intro or lab when we get on it?
It should be lab. You
Yeah.
go to lab. You should go to lab. All right, so let's talk about what you just saw right here. Okay, what did we discover in this lab of importance? So if we take a look at this. So last class, we talked about the difference between series and parallel circuits, right? So series circuit, one path, everything is the same. In a parallel circuit, multiple paths. Now we want to take a look at what is the relationship between
Ma'am, is there any way to let CJ back in?
who? CJ? Is he waiting?
It said you kicked him and won't let him back in.
Ben should have come in. Ben, are you with us?
He is. He's on mute.
I don't see CJ in the waiting room.
Well, it's because it won't let him in because you kicked him.
What do you mean I kicked him?
He said you kicked him out.
I didn't kick anybody out. He was in the waiting room.
I don't know. Never mind.
Tell him I'm not seeing him in the waiting room. Now he was the reconnecting, and I kept admitting him, and then it kicked him back into the waiting room. Okay, so getting back to this, tell him, so it's not letting him log in at all, Brock?
It says you kicked him out, so it won't let him in.
No, I did not put him in. I didn't remove him. That's going to require me to go to enable waiting room. I have no idea what I have to do to, I'm not seeing him anywhere.
You probably have to restart it.
I'd have to restart my meeting, I guess.
Mm-hmm.
All right, tell him I'll get in touch with him after this.
He emailed you is what he said.
Okay. Okay, what is the relationship between voltage, current, and resistance? Okay, that's what you were determining in this lab. So what we found in the lab is if I graph voltage and current, you got a nice straight line, right? The slope of that line is equal to 1 over the resistance. That's what the data was showing me in the lab. So as I collected the information from that lab, that's the data that I got. Voltage and current are related linearly, and the slope was equal to 1 over the resistance. So for me in the lab, the resistor was 10 ohms, okay? So what this means, if I put that of the form y equals mx plus v, my y is current equals the slope, 1 over resistance, times the x-axis voltage. So multiplying both sides by the r, you would get R times I equals V. That is what is shown in your data that you did in this lab. So rearranging that, we really typically write it as V equals IR. This is known as Ohm's law. V equals IR. Okay, what is the relationship between voltage, current, and resistance? This is what you should have derived in the lab. So as I was showing you, I got a nice straight line. I saw that the slope of that line was the inverse of my resistance. Okay, this is the slope of a straight, or this is the equation of a straight line. If I equate that to my graph, I can derive Ohm's law. So what Ohm's law is telling me is if I change the voltage in the circuit, I will change the current. If I change the resistance, I will change the current. But let's go back and take a look at one of our labs here. Let's see, I'm just going to do this. Okay, let's look at this second circuit. Okay, what doesn't make sense though is if I take a look at these two circuits, I am getting much more current in the second one than I am in the first. These two light bulbs here are the same as these two light bulbs. So what does it mean if voltage is equal to current times resistance? When I have the same stuff in the circuit, then I have different currents. So something must happen in terms of resistance when I connect light bulbs in these ways. So if I connect light bulbs so that they are in series, it appears that the resistance total increases because I get less current coming out. Over here, when I connect light bulbs in parallel, it must mean that the current or the resistance decreases because more current comes out in the circuit. So that is the last equation that we want to write down under our series and parallel rules. In a series circuit, when you add things, it has the effect of increasing resistance. In a parallel circuit, when you add things, it has the effect of decreasing your total resistance. Okay? So from your notes from last class where we listed series and parallel rules, I want you to add to that. First of all, hopefully you have this written down. In our series and parallel, so I'm going to keep Ohm's law up. And if we talk about a series circuit, and then our parallel circuit, in series, we found that our total voltage splits up. We found that our current is all the same. But what we need to talk about is the resistance. The total resistance that the battery sees in a circuit is equal to the sum of the resistance of each element in the circuit. So if I have 10 ohms, 10 ohms, 10 ohms, I'd have 30 ohms total. If my total resistance is high, my current is going to be low for the same battery. So these two have an inverse relationship under constant voltage. So if I have an inverse relationship under constant voltage, then that makes sense. But in parallel, when my voltage is the same, remember across each branch, So remember in parallel, 1, 2, and 3 are branches, not each individual bulb. Our current splits up. Right? But our resistance adds in a reciprocal way. And what that means, 1/10 plus 1/10, the more things I add, the smaller my total resistance comes. So that's what I want you to get out of that today. The more branches you have in a parallel circuit, the lower the total resistance. Hopefully, oh, can't see that too well, huh? The more branches you have in a parallel circuit, the lower the total resistance. The effect of adding more things in parallel is that you decrease the total resistance that is there. Okay, the more branches you have in a parallel circuit, the lower the total resistance. Okay. Anybody writing any of that down? I hope so. Everybody's got that? Do I need to step aside anymore? Okay. So that is about all the information that I want to give you regarding circuits. We're going to talk a little bit about power, but for this weekend, what I want you to concentrate, let's talk about what type of circuit do we think we have in our house? What type of circuit do we think we have in our house?
Parallel.
Parallel, why?
Series. Because it's all different.
Because it's all different. Because what is all different?
Because like one light, when you turn on one light, not all light, just
Each light works separately. Right.
Yeah.
Okay, so I can tell we're all lagging behind. My voice is different than my motions here. So we have a lot of bad connections. All right, so with that said, if you have, that's exactly right, we want parallel circuits, which means every time I turn something on, I'm bringing in more and more current into my house. All right, so now what's true in a parallel circuit is simply that you are sharing positives and negatives. So what's happening in a parallel circuit, you are simply sharing positives and negatives. So if I go back here and I take a look at parallel, what's happening in parallel? Okay, so if I were to draw a parallel circuit, looks like this, right? And there's a light bulb, so we're going to ignore our switches. Here's another light bulb, right? What's true is I can just take this positive line, this negative line, and continue it. I do not have to connect them at the end. When I think about a parallel circuit, literally all I'm doing is plugging in to the positives and negatives. That's what I'm doing. So you simply are going to take a plug and you plug something in. Okay, there's a plug right here. When I plug that in, all that I'm doing is literally reaching into the wall and connecting one side to positive, one side to negative, plugging it in a light. One side is positive, one side is negative. All you're doing is putting a switch in there to separate those. So for this weekend, I want to begin building our houses. So for some inspiration, hopefully you guys can all see. Let me expand my video. I want you to begin thinking about how am I going to design and build my room. So what I would like to do today is assign you all a room of what you need to build. And for inspiration, here's an example of one. Out of a box, look how cute. There is a little room. Okay, on the side, I have my battery hanging. All I have to do is connect this battery to my positive and negative wires that are around here. So let me connect my wire. I didn't want to wear it out. All right.
Man, where am I supposed to get like all of those materials? Like,
That's what we've been talking about the last week. Christmas lights. Here we go. That's all that I have. So there's your room. Look at
yeah,
that.
but like you have like a fan and like
I know. So I
have a
made the
fan.
announcement. So here's a ceiling fan, here's a light, and it all works. So watch, I can come into the room. Oh, my blades fell off and you can hear it rotating. My light will come on. There's my light. I'm turning on my switches over here, right?
I can't turn my
Not
Christmas
only
lights on,
that,
I don't know why.
this is my fireplace. So
How
watch
long did that
this.
take to make?
Here's my fireplace. Aw, look, it's all lit up. So I put an orange light behind the
It's
fireplace
not fire.
to make it look like fire. It has a doorway, right? That's where all your switches should be located. There's the wiring on the back of the house, how we connect it, right? So your challenge is to build this. This is what I want to see from you. So Drew, where do I get all those supplies? These were stones out in the driveway. These are just, this is all cardboard, right? So I want you to be creative and think of things. Electrically, all you need is your Christmas lights, your batteries. If you would like to get a motor like this to make a ceiling fan, I put a whole bunch of Benedictine. Between now and Friday evening, you can go pick one up if you would like. Brock, you live closer to me. You can come to my house. I have them here too. So I'm welcome. You're welcome. I'll stick them in my mailbox so there doesn't have to be any interaction. If you go to Benedictine, all you have to do is go to the front desk. They have a box sitting there and lunch bags. So you can pick up a motor if it's something you want. But you do not have to, I'm not requiring it. It's just something fun to have. But before you can wire anything, what your homework is this weekend is drawing me electrical plans. So I want to see your electrical plans, and if they are drawn correctly, then when you build it, that should be a correct, it's easier. So I do not want any construction taking place until you build, until you draw your plans. So what do electrical plans look like? So what you will find on Blackbaud is I will share with you something blank like this. All it is a blank floor plan, okay? Looks like this. It's a square. So no matter whether you are using a shoe box or a regular box, you just have this square. Okay, so I'm going to try to mimic that square up here. And I'm going to show you how to draw an electrical plan. So on your notebook paper, just sketch out a big square. And the first thing that you need when you are designing your house is the power. So we already decided we're going to use parallel circuits, right? So we're going to put in our parallel circuits. We're going to put in lights. We want switches. You may or may not want a ceiling fan. So let's begin on how are we going to draw these, all right? So let's take a look at that. How do I draw electrical plans? So I'll try to draw this as evenly as I can. So you begin with your box. All right. That box and the walls in your house have depth to them. So what I sent you blank is a square that looks just like that. That's representing your room. The first thing you need to do, and I highly recommend that you color code this, so find crayons, markers, something of different colors. Let one color equal positive and one color equal negative. So if my red is positive, Again, in a parallel circuit, you simply have a positive and negative connection, and you're going to connect across those. So what I have to do in my floor plan is put in positive and negative all the way around my walls. So basically, I'm going to start with my positive and put it in between my walls. So since we are making this very simple and we're not using a lot of wire, I'm just going to put it on 2 walls. Next to that, I'm going to bring the negative. So here's my negative line. And you can draw it right over top of your walls. But literally, this is what's in your house. You have wires behind all of your walls, 1 positive, 1 negative. Now your job is to tap into that. All right, Jack, what's one thing that shows up in all of our rooms? What do we have in all of our rooms?
Light switch
A switch. And Jack, where would a switch be located?
on the wall.
On the wall, specifically near what?
Outlets.
Your switches aren't necessarily near outlets.
Doors.
Doors, right? So when you walk in, you definitely want your switch near your door. So when we go in, first of all, you have to decide in my house. So here's my little house. So there's my room. So what we're drawing is like a top view. I'm looking at it in this direction, right? So there's all my things. I want to draw, how do I have to connect these wires? That's what I'm going to be drawing. So when I take a look inside my box, I put my door on this side of the room. I have a window on this side. So I want you to have 1 door and 1 window in your box. So the opening, of course, would be in the front. So you have to decide where you want that. So let's say this is where I put my door. A symbol for the door would look like this. Let's say I want my window over here. A window takes on a look like that. That's how you would symbolize a window. So my door, my window. If I want to put a switch, I should put that next to my door, right? I'm looking for my blue. And I specifically should put it on how the door opens. So this is where I'm going to put my switch. So use your symbols. I'm going to move it away from the wall just so it doesn't get too congested right there. And there's my switch. Good. Brendan, what would that switch be operating?
The light,
The light. Where do we usually have the lights?
the ceiling.
Right on the ceiling, right in the middle, right? So I'm going to put my light. There's my symbol for my light. All
Looks
right.
like an egg.
Looks like a mad face mouth, right? All right, so that's your symbol for a light. The other thing that's going to show up in the room is outlets. Your symbol for an outlet is like a plug, looks like a plug. Some might have an outlet on each wall, something like that, right? Now, if you want a fan, put the fan here as well with another switch. Let's operate those with 2 separate switches. So decide what goes in your room, all right? I'm going to assign you all a room by the end of class here. Pay attention to my time. And then you guys all have to decide what goes in your room. All right, so let me finish drawing these. So we had, if I could hold you back just a few minutes. If I was over here in my circuit and I added a switch, right, a light that operates off of a switch, and it was in the lab, it would look like that. So what I'm showing here is I leave my positive, I go to my light. I leave my positive, and I can use any positive anywhere. So I'm going to use it right here. I leave my positive, I jump over my negative, so I have to show that those are not connected. And I go to my light. So I take a line and I go down to my light. When I leave my light, Brock, where do I go when I leave the light in my circuit over here?
Where you go?
Here's positive, I went to my light. When I leave my light, where do I go?
Negative.
Not yet. What's this?
That's open switch.
The switch. So I leave my light and I go to my switch. Here's where I leave my light. Here's my switch. I'm going to draw that in a neutral color because it is not connected to negative or positive. I just go back to my switch. So here's my line. I go back to my switch. Drew, when I leave the switch, where do I go? When I leave my switch, Drew, where do I go? Is he still with us?
Is that just the battery right there?
Okay, what part of the battery?
The negative side.
Negative. Very good. I leave my switch and I go to negative.
Sorry, I was
Here's my
muted. I didn't
switch.
realize.
I leave my switch and I go to negative. Anywhere. Here's negative everywhere. So I leave my switch and I go to my negative. And that's it. And that's how my house should be connected. It doesn't necessarily look like this, but it is connected like that. All of your outlets simply connect to positive and negative. They don't connect across. You simply run a line from positive to negative. Like that. I'll let you think about the fan. It should be connected exactly as the light. So for homework, gentlemen, I want you to arrive on Monday with a floor plan drawn for a room in your house. Okay? Let's see, where do I have that written?
Can I see it?
Need to assign you each a room. Okay? Any preference?
Yeah, can I see
Anybody
it?
wants the bathroom?
Or bathroom.
Brock, you're doing the bathroom?
Yes.
All right.
Oh,
No hike.
All right, who wants the, I'm gonna actually have to have probably 2 bathrooms. Any other takers on a bathroom?
I'll do it.
Oh, Jack and Brock. All right, then I need a bedroom. Bedroom, Brendan? Okay, I'm gonna need multiple bedrooms. Ben and Matthew, I can't hear. Oh, Ben raised his hand. Ben, you're on a bedroom. So Brendan and Ben, all right, kitchen. Who wants a kitchen? That's gonna be a tough one.
Frankie,
Drew, no takers?
Frankie wants it.
We should give it to Frankie?
Yeah,
I think we should give it to Brock.
what? Already got a
What?
bathroom.
Okay, that leaves a family room.
I'll do a family room, ma'am.
Drew, you're gonna take a family room?
Sure.
That's
So like a living room,
Yeah, living room, den.
like what you made.
Yep, living
Okay.
room, den, family room. How about a garage? Matthew, I'm gonna put you on that one. And then we also have CJ. I'll think of CJ. All right, so each one of you have that style of a room. In your house, pay attention to that room. What's in it? Do you have a ceiling fan? Now, if you don't go get a motor, I don't want anybody going if you aren't comfortable getting out and doing that. But if you would like to have the ceiling fan, it's pretty cool to wire. But your homework this weekend, gather those supplies, start gathering things, start gathering artistic things, fabric, materials to be able to put things together. Number 1 is your circuit diagram. Secondly, if your labs were not done correctly, you should redo them. The latest I'm accepting them will be on Monday. So priority is your circuit diagram for your room. So decide what goes in your room and draw me the electrical plans for that. You'll have to scan it and send it to me. Okay? And then we'll build live next week so that I can talk to you if you're having trouble. That will be my plan. All right, gentlemen. I appreciate your patience today. It's been frustrating the last couple of days with our connection. Any questions from you guys? So redo labs if you did not do them correctly. I'll give you a grade on what you have, but I'm giving you an opportunity to earn a better grade if you did not do it correctly. That second lab should be very, very quick if you didn't do that correct. Draw your electrical plans, gather your supplies. Okay, so Drew, if you can't find Christmas lights or anything, they are available at Benedictine if you can get over there to grab a bag. If you
I
can't,
have Christmas lights. They're just weird.
okay, make sure you're allowed to cut them up because you're going to ruin them. All right, boys, thank you again for
Oh,
your
Miss
attention.
Rosenweaver,
Yes, Jack.
I'm gonna be out of town this weekend.
Can you draw while you're traveling?
Oh, I can finish that right now. Yeah, I can draw right now.
Yeah, I mean, you have today, tomorrow, you have plenty of time, right?
Mm-hmm.
So get it done before you go, I guess.
Okay. I don't know if I'll be in class on Monday or not. Probably not.
Okay, okay. Well, on Monday, I'm going to look at everybody's plans and give advice. So I
All right.
wanna
Well,
know
I'll just email a picture to you.
okay. Yeah, that would be great. And then I can make comments on it.
All right.
Okay.
See ya.
All right, bye.
All right.
Brendan, any particular questions?
No, I'm good.
Okay, smile.
I have a couple questions, ma'am.
All right, Drew.